In lecture video 8, I would like to talk with you a little bit about the unfortunately named electric potential. The electric potential is a very useful concept, and it's a scalar, so the math, again, is a little bit preferable to the way that we would have to deal with things like forces and fields, which were vectors. But unfortunately, electric potential doesn't have an analog for me to draw back to physics 140 about, and the name of it sounds a lot like potential energy. So it's sometimes a little bit difficult for students to wrap their heads around conceptually. Once you have, I promise the mathematics of it is very useful. So in mechanics, what we didn't do, but we could have done, is we could have said there's such a thing as the potential energy per unit mass. And since the potential energy in a gravitational field is mgh, what would have happened is mgh over m would turn into gh. And gh could have told us something about a scenario, but generally it didn't. I think largely because G was the same in every problem that we did. It was 9.8 newtons per kilogram. We might have, depending on who you had, might have thrown in a couple problems about what if you're on Mars or some other planet where lowercase g is a different value. But generally speaking, G is the same thing every time. That gravitational field strength is just 9.8. So our focus from one problem to the next was always how has the height changed and how has the mass changed. In electrostatics, though, this idea of the potential energy divided by the charge is actually very useful. Since the electric potential energy between two charges is k times the q1, q2 divided by the distance between them, if you take that and divide it by one of the charges, you wind up with the value kq over r. And kq over r is the electric potential around charge capital Q. And it happens to be equal to the electric field times R, except usually we don't use R in that situation. We usually say the electric field times distance d. Again, the potential energy per unit charge is what we call electric potential. I do want to point out that if you are comparing the electric potential between point A and point B, the potential difference, the electric potential difference, is called voltage. And that's a term that you're probably more familiar with in terms of circuits. But at the atomic level, the voltage might not be used as often as the term potential difference. So you want to make sure you're familiar with the electric potential and the potential difference. Again, not using the word energy in either of those terms. The units for volts are volts, and that's handy. The units for electric potential is also volts, because it's basically the same idea as voltage. And 1 volt is 1 joule per 1 coulomb. The analogy that I sometimes give is if you take a look at these two images that are here, it says it's not to scale, but imagine 100 kilograms, which has been lifted to a height of 1 centimeter, and then 1 kilogram that's been lifted to a height of 1 meter. That's 100 centimeters. The potential energy between these two situations is the same. One of them is 100 times more massive, and the other one is 100 times higher off the floor. So again, the potential energy is the exact same, but there's definitely something different about these two scenarios. It's just that when it came to potential energy versus kinetic energy, it didn't matter to us. And with electricity, there is a reason why the difference would matter in terms of potential energy per unit charge. I'd like to use this slide to remind you, again, a change in potential energy related to a change in kinetic energy. And it says the change in potential energy is equal to the negative of the change in kinetic energy, because what we mean by that is when the potential energy goes down, it's usually associated with the kinetic energy going up, especially if what we're talking about is just the field doing the work. So as you throw an object up in the air, its potential energy increases, its kinetic energy decreases. Well, similarly here, if I were to place a charge Q at point A in this electric field and allow the field to do the work of accelerating this charge from point A to point B, then what I would find is the potential energy of the charge, which is equal to the negative of the work done by this E field, it would therefore be equal to the negative of the force that the field is pushing on it times the d, however long that distance is from A to B. This is the work, force times distance. The force exerted by the field on a charge is the strength of the field times however strong the charge is that you put in the field. So the change in potential energy for this charge in this field is the negative of its charge value, Q, times the electric field strength, times this distance. What this would do is accelerate the charge, and so again we would see that as the potential energy drops, the kinetic energy goes up. The potential difference or voltage of this scenario is capital V, delta V, equals negative times the electric field strength times the distance through the electric field strength. It's not often that I see someone confuse this delta V with delta V, the change of velocity from Physics 140, but I do want to emphasize lowercase v velocity, uppercase V is where we're talking about voltage. So delta V is the voltage or the potential difference between 2 points. And this equation will be on our equation sheet. Any charge, capital Q, by itself will distort the space around it and create an electric field. And we already have an equation for that. That same charge, capital Q, has associated with its electric field, and therefore associated with it, a electric potential. The voltage around an individual charge Q is K times big Q divided by R. So if you know how far away you are from a given charge Q, then you can calculate what the voltage is between that point you're talking about and the charge Q. I am positive that some examples would go a long way to making everyone more comfortable with this concept. Before we do examples, I want to point out a couple things really quickly. This is an image of a positive charge, capital Q, and I've already shown you what the electric field looks like around that. That's these blue arrows radiating outward in every direction in an r-hat direction. We had an image in a previous video talking about these concentric circles. The concentric circles around this symmetric electric field are lines of potential. Anywhere on this line, this circle, all the way around this charge, K times Q divided by R would be equal, because the K is a constant of the universe, the Q doesn't change, and R only changes as you move farther and farther and farther away from this charge. So on this circle, you're not moving farther and farther away. That means that the voltage anywhere on this circle is the same. And the voltage anywhere on this circle is the same, or more precisely, the electric potential is the same, because the voltage is the difference in electric potential between 2 points. These lines are therefore referred to as equipotential lines. Equipotential lines are often compared to the lines on a topographical map, because if you were to go out on a hike and specifically trace the line on a topographical map, the whole point of the topographical map line is to show you areas that are at the exact same altitude. So on a hike along that line, you would not change your altitude at all. Similarly, as you trace the equipotential line along here, no work is needed to be done. You're not increasing or decreasing your potential energy of your charged object that might be placed here. In order to calculate the electric potential at a specific point in space, you would find the electric potential due to charge 1 and due to charge 2 and due to charge 3 and due to charge 4 and add them all together. This is even easier than when you were trying to do this with potential energies, because the equation is just K times Q1 divided by R. So for example, if I gave you this point here, what you would need to know to calculate the potential there is you would need to know the value of each of these Q's and each of these R's. And you would just do this equation, K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3 plus K Q4 over R4. If you are never comfortable with that big sigma in your mathematics, that's what that means, is that you would do it repeatedly and add them all up.